Okay, we were discussing thermal spraying, and so we have seen the four section in which the process can be divided. We skipped this slide last time. Now it's time to start the discussion. I told to you that they are very important uh, surface engineering methods, those which are classified under thermal spray, uh, and they are controlled by quite a relevant number of processing parameters, which can be directly linked to the coating quality, that is, to the properties of the coatings and thus to the performance in surface of the coatings. Here you have a list of some of them. They can be as high as 40, depending on the, let me say, four sections that were represented on the previous slide. So for what it concerns the heat generation, that is the energy source, we do have to take in mind which is the type of the energy source which is used, that is how the energy is generated, which is the gas composition, as we will see later on, and their flow rate, which is the temperature, which are, if any, and they need sometimes, cooling properties, and the way to generate, if it is present, the electric arc. Then we do have this section of the material feed, that is the materials in forms of powder, which is used in order to fabricate the coatings. And so we have, for example, the particle size, the particle shape, the particle distribution. Look into the feeding of the particle itself inside the plasma or inside the plume, let me say, generally speaking. We do have also to consider which kind of carrier gas are going to be used, which are the flow rate, that is the velocity of the gas itself. For the material spray, that is the part of the process in which the gases are going to interact with the particles before the fabrication and the realization of the coating, we do have to know, and it can be modeled by using the most, let me say, advanced fluidodynamic approach, numerical, I mean, which is the gas exit velocity and the gas velocity distribution, the temperature distribution of the gas. Then, since the gun, it's, as I told to you last time, controlled in movement by using a robot, we do have also to consider which are the spray gun movement, and thus, together with the previous one, which are referred to the gun and to the gas exit, also the particle velocity and particle temperature, as well as the trajectory, which are influenced by the exchanges, which are, let me say, thermal exchange and kinetic exchange with a gas outside the torch. And then regarding the material deposition, we do have something to cover. This something is called substrate. And so the substrate type, the preparation of the substrate is very important for the final coating quality, as well as, for example, the possibility to move this substrate, the possibility to cool down the substrate depending on the temperature which are reached on the surface, and all the mechanisms which are related with the particle impact, splatting, impact, and coating fabrication are important for the coating qualities. So you see there are many processing parameters. If we want to, let me say, just make a comparison with another techniques, not for coating, but one of the technique which is very important for components in your field, for example, high isostatic pressing technique, well, there we do have, well, the materials, that's all, that's obvious. But essentially two processing parameters which are very important, that is pressure and temperature. Here we can reach very higher number of processing parameters which must be monitored, which must be selected during the fabrication process, and which for which we do have, obviously, and I'll tell to you some guidelines in order to make the proper choice. we already have seen last time, according to the let me say energy source, this distinction according to the German standard in thermal spray by gas, where we do have combustion processes, and thermal spray by gas discharge, where we have essentially plasma processes. And we have already seen, as it will be clear in the next discussions, that the most important techniques for us, at least for our application, not for all, but for us, are the high velocity oxygen fuels for the thermal spray by gas, and plasma spraying for thermal spraying where it exists an electrical gas discharge in order to have the heat generation. Applications, then we will see obviously the processes in order to let you have an idea on how wide is the application area.
Professore, non so se è un mio problema, però a me non vanno più avanti le slide, cioè è bloccato sulla prima proprio.
Qui le muovo, anche gli altri colleghi che sono in linea vedono sempre la stessa slide?
Sì, prof.
E che devo fare adesso? Perché qui si muovono. Tutte le volte ce n'è una. Provo a interrompere la condivisione e a ricondividere, va bene?
Ok. Right now it changed.
I know, but it's not fine for me. Can you see now the slides which are going to modify?
Yes, Professor, they are changing.
So this slide we already discussed last time. I was telling to you, let's have a look to the application in order to have an idea on how wide is the potential and the application of this family of technologies. We do have examples of applications for coating fabrication, which can give to the components proper wear and or corrosion resistance. And this is used, for example, in mechanical, chemical, aerospace, or also textile industry engineering. And some materials which are quite common, they are not the only one, but quite common, in order to have wear and corrosion resistance, we can have a use essentially for corrosion of metallic-based coatings. And in this case, we do have superalloys, which are nickel or cobalt based, with other elements added, like, for example, chromium, boron, silicon, carbon. Or we do have the family of CERMET, that is ceramic metallic alloys, all in the form of powders, used in the form of powders in order to fabricate the coatings. And here, one of the most important, essentially for the aerospace field, are those CERMETs which are based on the use of a ceramic phase, which is tungsten carbide, the first of the list, okay? Or tungsten carbide in a metallic matrix, which is usually cobalt chromium matrix or nickel chromium matrix, even though they exist also some other examples in which other ceramic different phases from tungsten carbide are used inside metallic matrix. The matrix is more or less almost the same, which are, for example, chromium carbide, Cr3C2, or titanium carbide. Then, in order to contrast corrosion and wear together, being this class of materials not susceptible of electrochemical corrosion, we can have also coatings made by ceramics. For example, chromium oxide, for example, alumina, titanium oxide, essentially oxide-based ceramics. I mean, when we do have non-oxide based ceramics, one of the items is that usually non-oxide based ceramics, if they see oxygen during the fabrication process, they undergo a deterioration phenomena. Just an example, if you have carbon inside the non-oxide ceramics and carbon see oxygen, it can form, for example, carbon oxide, carbon monoxide, carbon dioxide. So there is a degradation. So it is quite difficult in this case. I would say it is impossible in this case, in presence of oxygen, to define a melting point of a non-oxide ceramics if it reacts with the oxygen in the atmosphere. And so in most cases, where this limitation applies, and this applies for tungsten carbide, this applies for titanium carbides, this applies for silicon carbides, it applies also for non-oxide ceramics, not carbon-based, like silicon nitride, for example. Well, usually they are used in the form of cermet because they do not undergo a fusion phenomena, but the phase which is going to be melted in order to fabricate the coating is the metallic matrix, and thus the ceramic particles, they still remain solid and are distributed inside the coatings after coating fabrication due to the fact that we have a liquid phase which is represented by the metallic matrix. Then another field that we have seen many times, but we need to mention it again, which is proper for energy, generally speaking, industry, and also aerospace, is the fabrication of thermal barrier coatings based on partially stabilized zirconia. But we can have also high temperature resistant corrosion coatings fabricated by these technologies, essentially for the oxidation phenomena, which are in this case metallic based, and which are essentially those we have already seen as coatings used for the fabrication of the bond coat in thermal barrier coatings, that is nickel chromium coatings, so nickel, cobalt, chromium, aluminium, yttrium based metallic powders. But also in the how to say, surgery industries, or something which is related with medical application, we do have coatings on implants, for example, because we can fabricate by these techniques biocompatible coatings, which can be made by metal materials. One of the most important biocompatible metal is titanium, but also stainless steel is used, essentially titanium, but also some other formulation, that's just for your knowledge, which let me say, to some extent, they can reproduce a sort of synthetic bone, which is called hydroxyapatite, is the last component there, which is a material which can be sprayed with these techniques in order to have, for example, in implants, surfaces which can be well implanted because they have biocompatibility properties. If we look to the area of application, the aero engine manufacturers are the biggest users of this kind of thermally sprayed coatings. In both cases, I mean in the case of the fabrication of the original components or equipment, things, just to say another time the same thing, the thermal barrier coatings, for example, but also for repairing when you have damaged components. And in this case, we can have wear corrosion, oxidation resistant coatings, thermal barrier coatings. We will see clearance control coatings, essentially the abradable family of coatings, which are used on the top of the blades in order to diminish the lack of gas and have the possibility to have a rotation of the blade without any problem for its lifetime. The automotive industry is having essentially the aim to reduce the fuel consumption, to reduce the quantity of pollutants, or to increase mechanical and again corrosion and wear resistance of the components are also an area in which these kind of coatings are widely used, obviously for high added value application, not commonly, okay? For example, outside diameters, as I brought to you, of piston rings are treated in this way. They do have coatings on the surface in order to reduce wear and thus to reduce losses and thus to increase lifetime of the component. They are used, these coatings, also on lightweight engine blocks by special technologies which are called rotating plasma, because the gun is rotating in order to cover the cylinder. Essentially, when we are going to use light alloys, why light alloys? Something which is very near to aluminum, because the melting temperature of light alloys is low, and so we need to increase, apart from wear, apart from corrosion resistance, also the possibility to have proper temperature inside the engine blocks, because you know that they control the performance of the engines, as well as they are used, I mean, these kind of coatings in a lightweight brake disc. For example, in the case, and also this you cannot find it on common vehicles, but you can find it in vehicles which are, let me say, a little bit more expensive, including also for the lightweight engine blocks, Formula One vehicles, okay? In the case of brake discs, there are examples of aluminum matrix composites reinforced, for example, with ceramic particles, which are coated by using ceramic coatings in order to have both the desired friction properties and the resistance to high temperature, which is developed during the braking phase. But surgical implants, I told to you before, other application, rolls used in the paper fabrication, cylinders, very long cylinders, some meters of diameter and some meters long, they are coated with wear-resistant coatings in this way, because paper during the fabrication phase is a very aggressive material for what it concerns tribological loads applied to the surface. And obviously, if you have a surface of the rolls which is damaged due to wear, the quality of the paper you are going to fabricate is not a good quality. And so you need very hard surfaces, and usually they are fabricated with the principle to have a sort of composite materials. I mean, having the substrate, the cylinder, which has the function to resist to loads, to support the surfaces for which the desired hardness and friction resistance, generally speaking, is given by using a thermally sprayed coatings. But also other, for example, chemical industry pumps, where you have very aggressive fluids, and you need to give to the materials a good corrosion properties without using that materials as a bulk for economic reasons, and also for the sake of simplicity for fabrication. For example, the wall component are treated by using thermally sprayed coatings. Now, let's have a look just to the fourth part of this diagram. In order to enter a little bit in our topic, the fourth part is this one, where I have reported the two most important, as we have discussed before, processes for us, for our application: combustion-based processes, that is the high-velocity oxygen fuel processes, and plasma spray processes, which are divided here in the two most common technologies. They are not the only one, but they are the two most common technologies available. The first one, which is called the VPS, that means vacuum plasma spraying. The second one which is called APS, which stands for air plasma spraying. What does it mean? It means that, well, the high velocity oxygen fluid we will discuss, but it has a combustion processes in order to generate the head source. The plasma spray technology has an electrical arc discharge in order to generate a plasma that we will define. And this happens inside the torch, inside the gun. Well, in the case of plasma, this torch can be inside a confined area, okay, a confined vessel. In that case, if we have our pumping unit, for example, we can make void to a level which is not very, very high, but is sufficient, for example, to remove oxygen, which can interact with reactive materials during the spray process. And in this case, we do have the process which is called vacuum plasma spraying. Instead, if the torch is working in air without any confined vessel, this is the technology of air plasma spraying. Before discussing a little bit these figures, because they are very important, let's say how to say logical things. Obviously, if we want to compare at a glance the cost, the plant cost, if you want, the execution cost of the process of the vacuum plasma sprayer with respect to air plasma spraying, we can expect that air plasma spraying is, let me say, less costly than vacuum plasma spraying. We do not have the vessel, we do not have the pumping units, we do not have to control the level of void, etc., etc. And thus, if we need to spray, for example, a ceramic materials, an oxide-based ceramic materials, for example, our partially stabilized zirconia, or for example, as wrote before, alumina titanium powders, well, our first choice, if possible, and this is possible due to the figures that we will discuss now, is not to use the vacuum plasma spray technology, but is to use the air plasma spray technology. And the reason is very simple. One is the cost, okay, but the second one is that we can get good coating quality, because if we are going to spray an oxide-based ceramics and our spraying process is performed in air, we do not care about oxidation phenomena on the starting materials, that is on the starting powders, that is on the powders alumina, titania, or plasma, or partially stabilized zirconia, because they are oxides. Instead, if we need, for example, or if we select to spray a metallic alloys, okay, nickel, chromo, boron, silicon alloys, for example, well, in that case, the question on which of the two technologies must be used to have a better coating quality is worthwhile to be discussed, because a metallic alloys can go under oxidation phenomena if the molten particles see oxygens before coating deposition. And this cannot be neglectable, because when we start with a metallic defined composition of the alloy, and then we experience oxidation before coating fabrication during spraying, this means that the coatings that we are going to fabricate it has not the same chemical composition of the starting powders, but it has another composition, it's another material. And so in that case, it's worthwhile to be, let me say, taken into right consideration the possibility to use vacuum plasma spraying. Well, if we have a look at, again, to a glance to this diagram, you see that in the red column, they are going to represent the maximum temperature which can be get, not by the material, but by the gas or by the heat energy source, let me say in generally in this way, whilst The blue color is going to define which is the maximum particle now powders velocities which can be achieved for the best performing technology belonging to these three areas. And what we can see that if we are looking to plasma spray technologies, that is this one, and that's not a mistake, we can reach temperature of the gas phase that will be a plasma as high as 15,000 Celsius. That means 15,000 Kelvin, because 273 does not make any difference, okay? And so these one are processes very hot, and we do not know any materials which cannot be melted in principle by using this temperature, because we do not know any materials having melting temperature higher than 10,000 Kelvin, okay? So these technologies, the plasma-based, they are suitable to fabricate coatings with any materials known, if we look to the possibility to melt the powders, unless the starting materials does not have a stable liquid phase, such for example, silicon carbide or silicon nitride, okay? If we look to the HVOF instead, which is a combustion-based process, let's have a look to the maximum particle velocity which can be achieved. It is something around 700 meters per second. A single particle is traveling with a maximum velocity, which is something very near and sometimes also higher. That depends on the type of gas used in order to have the combustions, 700 meters per second. Instead, here we do not have, for the HVOF, plasma generation, but we do have the energy source which is given by combustion, and so the maximum temperature, when it goes well, very well, they cannot reach values higher maximum gas temperature, okay, than 3,000 Celsius. So the combustion-based process, they are not so suitable to fabricate coatings by starting with ceramic powders, because we know that this, even though some examples they exist with very fine powders used as feeding powders, but generally speaking, because we know that our ceramic-based materials, they do have melting temperature which are going to approach 3,000 Kelvin or 3,000 Celsius. Think to partially stabilized zirconia, it has something which is around 2,700 Celsius. And so the energy source in the HVOF is not able to melt the single powders. And if we do not melt the powders and we spray on the substrate, we will have impact of solid particles with a solid substrate. We will not have any coatings, but just abrasion on the substrate. And so we say that the plasma spray processes I put together, they are, let me say, characterized essentially by high or the highest values in temperature. Instead, the combustion-based processes, they are characterized by the highest velocities of the particles before impacting the substrate. And this, for example, this is the reason because of when we discussed about thermal barrier coatings, we said if we want to select in the field of thermal spraying processes, the more suitable technologies to fabricate the ceramic zirconia-based top coat, we use plasma. The reason is the temperature. But if we want to select the most suitable technology to fabricate the M-acrylic bond coat, we use the HVOF, because with that metallic mixture, that one of the bond coat, the M-acrylic, the maximum temperature which can be reached by the HVOF are suitable to melt the alloys, and we take advantage from the very high value of the particle velocity, which is able to give to us very dense coating. Instead, if you remember, we said when we use the plasma spray, and especially in this case, in this example, air plasma spray to fabricate the top coat, we do have a residual porosity, which is something around 8, 10, 5, that depends percent, but not 0. And so we are obliged to use the bond coat in order, and this is just one function of the bond, to stop the oxygen diffusion and prevent oxidation of the superalloy if we have in mind a combustion chamber, or we have in mind a four-stage turbine blades. The reasons of the choice of these two technologies are in these features, main features of the processes. You can see also another thing which is quite interesting. First of all, this very high value of velocities, they allow to us to understand as, generally speaking, with the exception that depends on generally states, with the exception of APS, generally speaking, they are very noisy processes, because we have velocity which are higher than 340 meters per second, okay? And this is one thing. The second thing, if you compare the VPS velocity, particles obviously, and the APS particle velocity, you see here that with APS, more or less, we can reach something which is around 300 meters per second. With a BPS, we can achieve something which is near 500, so higher than the speed velocity, the speed sound velocity. And which is the reason? Because we can expect that even though, for example, we use the same torch, as we will see, we use the same gases, plasma gases, etc., we use the same powders with the same initial shape and size, that is granulometry. In the case of VPS, we can experience particle velocity which are higher, because is the plume which comes out from the gun does not make any resistance, because we have made void. Obviously, that plume will be longer, and the losses will be lower. That is, the particle velocities can be expected higher. So VPS as also with respect to APS, not with respect to HVOF, let me say the advantage, generally speaking, to let higher values of the particle velocities, that is, lower residual porosity on the fabricated coatings, higher than HVOF, but lower than APS. And this is the third reason, because of, if we used, and we use it, because that's good, that's enough, APS, for the fabrication of partially stabilized zirconia top coat, we do have porosity values residual as higher, as I told to you before, in the range 5 to 8 to 10%. If we fabricate by fabrication, let me say, of the top coat by VPS, we should have values of porosity lower, of the order of some point percent, but they are still too high in order to prevent oxygen diffusion, and so we select the use of APS and then put together the double system with the bond coat. and the top coat. So these are the main feature of these two processes. And so if we want to again just have a look to the first three, if we want to put some let me say qualification words near these three technologies, two technologies, one is divided in two. For the HBOF, we can say that we can expect a good coating adhesion to the substrate due to the high velocities of the particles, but also good coating cohesion, that is inside the coatings, again for the high particle velocity. And so low porosity and high wear resistance, for example. For the BPS, without oxygen, because it's a plasma made in vacuum, we can have high purity coatings and oxygen-free coatings, oxide-free coatings, in the case we are going to spray something which can be oxidized. For the APS, we can use a wide range of materials. We do not use this when we don't want oxides inside our coatings. And as we will see later on, this applies also to BPS. It's characterized by a high spray rate, that is high productivity, the possibility to make coatings very, very, very quickly. How the coating is formed? These are, let me say, general concepts which can be used for both the two classes of technology. We do have particles, starting particles, powders. These starting particles must be selected in average size, but also shape, but let's talk about size, in a proper selected way, because you should have in mind your, let me call it flame, what is going out from our torch. Then it can be also plasma plume. The particles are injected, okay, as we saw in the general scheme, and these particles are traveling inside the plasma plume, or inside the plume itself, not for hours, but for fraction of seconds, due to the high velocities. We have both in HBOF and in plasma. They are different, but they are still high velocity, higher than 300 meters per second. And so this means that the so-called dwell time, that is the time for which the single particle sees the high temperature of the plume, is not 1 day, is not 1 hour, is not 10 minutes, but they are again fraction of seconds. And this means that if we want to melt our particles, we cannot expect to use particles having 1 millimeter as in average size. Otherwise, we are not able to melt them. And this is the first problem, okay? And so we need to select diameter, average diameter, if we have in mind powder granulometry, which allow to us to melt the powders during the phase in which they interact with the flame. There is a second concept. The second concept is that, because if we look only to this, our idea would be, okay, let's select particles. Let me say one thing which is not possible, but just want to explain to you, having an average diameter of 100 nanometers, as small as possible. So we are sure that we melt them. Well, remember that we have another potential phenomena. I mean, if we go on to overheating because we have melting, then we can start a vaporization process of the powder itself. So we do have an upper limit, let me say, for what it concerns the particle average diameter due to the necessity to melt the powders. We have also lower limit, which we do need to overcome in order to minimize the vaporization after melting. And this results as a general, let me say, guideline, in average diameters which are a tenth of microns. 25, 30, 40 microns. This is the optimal granulometry of the powders which must be used with this kind of technologies. If we have a look to the average size, just to give to you another, let me say, concept, which are the most suitable for the HVOF and the average size, which are the most suitable for plasma technologies, I should say, and I say that for plasma, we are more or less around 40 microns as average diameter. Instead, for HVOF, we are around 20 microns as average diameter. Why this difference? Again, because if we remember what we have seen here, in HVOF, we do have two differences from the plasma. First, we do have lower temperature of the gas phases. And so we need with respect to plasma, lower diameter of the particles. But we do have at the same time also higher particle velocity, so a reduced time of dwelling of the particle inside the flame, and this led to, just to give to you an idea, to use powders for the HVOF which have more or less half the diameter of the same, of the corresponding, if you want, powders, when we have in mind the same materials, which are used for the plasma spray process. Then, what is going to happen? The powders are melted. Let me say, you have to think to a stream of powders which are projected by the flame. And so we have powders which impinge on the substrate and they allow to us to fabricate the coatings. But we have also powders which can in part undergo to a vaporization, because powders, they do have a granulometry distribution. They are not used monomodal powder size. So if I say 40 micrometers, that's an average, okay? And so this means that we can expect inside our particle distributions of the powders values which are lower than 40, but also some values which are higher than 40. So we can have phenomena of vaporization. For bigger powders, bigger than 40, for example, they could not be completely melted or well accelerated, and they could fall down with respect to the plume. So that's material loss. So there is also quite a relevant number, let me say, of dust during these technological processes. And the dust is not dust that we have in the air, they are particles fundamentally. And then for the part of the spectra of the granulometry distribution, which can well interact with our flame, the melted powders are going to impact on the substrate. They can split on the substrate, and then by subsequent split, you can fabricate the coatings of the thickness you desire, with the limitation that we will see later on of the thickness. We have already seen, or sorry, we have already said that these technologies are those belonging to the technological processes suitable for the fabrication of the so-called thick coatings. And thick coatings means coatings having a minimal thickness, which is something around 100 micrometers, and a maximum thickness, which is something, apart special cases, around 700-800 micrometers. So this is the range in which the window in which the thermal spray processes can allow fabrication of coatings. And why we do have the lower value, about 100 micrometers? Because you have a single powders here splatting, okay? Then you will have, let me discuss this on this slide. You have the single splat, which is this one. Then you have another splat, which is this one. Well, more or less, just to give to you an idea, when you have the liquid powders and they splat, day 8, okay, after splat, after the impact, is something around 1/5 of the original diameter, okay? So let me say, just to make a simple calculation, if we have 50 diameter, 50 microns as average diameter, and we put our attention on that, the single splat after impact has an age of something which is about 10 micrometer, okay? And the gun is going to be moved if you want to coat something having a specific shape. And so this means that you are not able to cover completely the surface, okay, just with a gun pass, but you need a certain number of passes because you could have, for example, this is the substrate, let me say, this is the fourth splat or the fourth powders, and the near, for example, will be here, okay? So here you have void, and so you need a second pass in order to close this, and the same applies also for the subsequent pass. And thus, again, as an order of magnitude, with the figures that we have seen, we need at least 4 to 5 passes of the torch in order to well coat our substrate due to these figures that we have discussed. Then what can be also happen? Well, that depends on the processing parameter, but depends also on the materials. One of the two most common defects which can be found inside these processes, obviously with a different, let me say, importance, depending on the fact we are going to discuss about HVOF or about plasma, for the reason we have seen, is that if we have a granulometry distribution of the powders, and so we can expect the optimal, let me say, results for the average size, the powders which are higher in average diameter, they are not completely melted, but they can be again found inside the fabricated coatings because they can be entrapped by the smallest powders which were melted and then solidified. And so we can have unmelted particles, for example. And this is one of the quality control parameter, very important, because the unmelted particle, let me say, is able, that depends on the material composition, but is able to represent some weak point inside the coatings, having in mind, for example, mechanical properties. Or we can have not a complete coverage, layer by layer. That means we can have, that's black area, voids inside the coatings. These voids inside the coatings are what we have already called before porosity inside the coatings. Obviously, if we are talking about HVOF, let me say the quantity of this void can be, if the process is well done, essentially neglected due to the high velocity of the particles. Instead, they can be present in the plasma sprayed coatings. And on the contrary, let me say, usually, since we use plasma for high melting temperature materials, the possibility to have unmelted particles is higher in the plasma spray fabricated coatings instead of the other class that we have discussed. Now discuss the plasma spray, then we will discuss the HVOF field. Plasma spray, the name plasma. The name plasma is linked to the fact that the energy source is a plasma. And you should know that plasma is the so-called fourth state of the matter. In this case, we are talking about a gas plasma, phase, which is obtained by using special gas, common but special, not all the possible gases, and which has the properties to have the number of positive charges, that is ions, equal to the number of negative charges, that is electron. And so the plasma, which is used inside this technology, is what is said being neutral, electrically speaking, on an average, okay? And when we look to the gas, which are used for generation of the plasma, then we will see how the plasma will be generated. We do have very few options. First of all, oxygen is not used at any time. Not because we cannot make a plasma based on oxygen, but because, as we will see, the gun is made of a solid materials. It has many metallic parts inside. The presence of oxygen will completely and suddenly destroy the gun, that is the torch. And so usually we use essentially four types of gases to have the plasma, which are hydrogen, then we have argon, then we have nitrogen, and then we have helium. And we can, in this kind of technology, generate a plasma only using one gas species, with the exception of hydrogen, or mixing different gas species. Among these we have mentioned, not more, not anymore. And the selection of the plasma, of the gas which is used in order to have our plasma, is strictly linked to the energy content that we do have after the plasma is formed and after the recombination phase, which leaves energy suitable for particle melting and for particle interaction with the fluid. And here you have an idea, that's a thermodynamic calculation, or what is going to happen in the case we use p-atomic gases, that is nitrogen or hydrogen, in which we do have a double dissociation, first in atoms and then in ions, or monoatomic gases like argon and helium. And you see, and if you have in mind this picture for what we will say later on, that the map of the temperature and as well as the map of the energy content is different from one to the other case. And so usually, with the exception of this one, we could think to use just nitrogen or just argon or just helium as a plasma gas, but usually, and that depends on the materials to be sprayed, we use a mixture. One gas in what will be used to form the plasma will be present at higher volumes, at higher concentration, and this is also called primary plasma gas. And the second one, because generally most of time, not all, but most of time, they are used mixture of two gases, will be in a presence, in a percentage lower, and this will be called secondary plasma gas. Now, okay, we have seen the temperature. How to generate the plasma? The gases which are going to start use at the beginning, they are not dissociated. And so they are forced to pass between two electrodes, which are inside the plasma torch. one electrode is a cathode. I will show to you a plasma torch later on. The other electrode is the anode. Okay, so if we apply a suitable voltage difference between the cathode and the anode, this is going to be present inside the torch. We can have the dielectric here, which is broken, and this means that we can have the formation of an arc, of an electric arc. If we force our plasma gas to pass where the electric arc is established due to the application of a voltage difference, generally we work with a current density constant, but that's equivalent, then the interaction between the plasma starting gas, the mixtures, and the arc is able to generate the dissociation and ionization phenomena which gave rise to the plasma state. This happens here, then this gas, to some extent, must go out from our torch in this direction, for example, okay? And by having a temperature and a velocity profile depending on the, and that's a matter for you, on the shape and size of the nozzle exit. Okay, so you can find, as you know, different configurations of the nozzle exit if you have Mach values higher than 1 or lower than 1 if you want to accelerate. And this is the basic nozzle is the de Laval nozzle, which is used also in this system. When the plasma goes out from the end section of our nozzle, where we reach here at the exit that values of maximum temperature, 15,000 Kelvin or 15,000 Celsius, it has, as I was telling to you, a velocity profile. Then the temperature will drop. We will have recombination of ions with electrons, energy which is released, and if we inject our powders in this area, not inside, the actual injection is one solution which can be experienced and is existing for the HVOF. But now we are discussing about plasma. If we put powders here where we generate the plasma, this will be completely closed in a moment. I mean, the space between the anode and the cathode. So the injection is external. And these powders, the powder same, will experience the thermal exchange, the kinetic exchange, all the phenomena which are then necessary in order to have our cooling. What to say here, and you see here, there is one important thing, cooling water, okay? Why cooling water? I mean, this system, then it is made by using water, distilled water, obviously, need to be cooled, because if we do have here 15,000 Celsius, we have said that we do not know any materials having a melting temperature as high as 15,000 Celsius or 15,000 Kelvin, but we need to fabricate these things. So we need to cool in order to allow to keep the temperature, and then we will see the solution, to keep the temperature as low as possible to avoid melting of our torch, okay? And so the torches in the plasma technologies, they are all cooled by water. This is the example. Then this is, let me say, a drawing. This is a real torch fabricated by one of the, it's not the only one, it's one of the most important, let me say, industries which design and fabricate and sell this kind of equipment, the so-called Metco. Sulzer Metco was the previous name. Metco is very active in this field, and so here you will find all the elements that are represented here, okay, in a schematic drawing. So you see here, here we have this is our torch. Our torch, more or less, is, let me say, 10 centimeter, is a cylinder, 10 centimeter in diameter, and something about 15 centimeter in length, so just a cylinder. Inside this cylinder, we do have the inlet of the gases which can be used, which are used to form the plasma. Okay, and you see here they flow through the annular space where do we have the anode and the cathode that we have discussed before. Oh, sorry, this one, you see, this one cathode, and this one, the annular space, is the anode. So this is the cathode and this is the anode. Metallic materials, because we need to establish an electric arc. We cannot think to use ceramic materials in this case, okay? And then I will be back. We have the nozzle. Here is not designed, the nozzle, for example, the Delaval nozzle. So we have the plasma, which is formed. We have the recombination area. We have the particle injection, the powder injection, which is essentially external. And so particles, they experience, when the parameters are well selected, this kind of trajectory, for example. And so they can be melted and they can be accelerated. They can be projected here where there is the substrate to be coated. But for example, this can let us understand how the flow rate of the gases which are used to transport the particles, as well as the size of the particles itself, are very important, because we could have, for example, particles which are making this, or particles which are making this, depending on the velocity, on the axial velocity, and that's depending on the flow rate of the carrier gas and on the diameter of the particle itself. And this one are not suitable to fabricate our coatings. Just the portion which is inside the plasma fume can result in the coating fabrication. Then what we see, you see here, if this is the anode, this one, and this gray part is the cathode, first of all, we do have to establish inside the torch an insulation between the two electrodes, otherwise it doesn't work. We do have the possibility, the necessity to cool, you see here, cooling water, and due to the fact that at the tip of the cathode, I mean, I am here, okay, there is the arc, which is formed. The charges, the electrical discharge, obviously implies that at the tip of the cathode, the temperature will be very, very high, okay? And so we can experience local melting on the cathode, even though we do have a cooling system for this part. And thus, coming to the materials which must be metallic, which must have a very high melting temperature, which is used usually for the fabrication of the cathodes, is tungsten, having a melting temperature, if you go on the periodic table of the elements, which is something a little bit higher than 3000 Celsius. So it's very high. But nevertheless, local melting can happen due to the localized electrical discharge. And so this means that these cathodes, they do not have an infinite life. They must be changed after a certain period of time that depends on the spraying process, which is going to be performed. And they are treated as spare parts, essentially as spare parts. And it is important to the substitution of the cathode when the geometry profile is very altered, because that implies not a good formation of the plasma system and thus of the spraying process. And the cathode lifetime, they are of the order of, let me say, 100 hours. Huh? But in order to coat, just to give to you an idea, in order to coat a blade, we can need, depends again, but just to have an idea, we can need something which is a spraying process, not as per all procedures, something which is around a couple of minutes. So this means that 100 hours, it's quite a relevant figure in order to process a significant number of components to be coated. Instead, up to you, just let me make a question, at least for the colleagues which are present here. This part, this external part, what we call here the anode, okay, also that one must be cooled. It's more simply to cool this with respect to the tip. Also in this case, we need to not exceed the melting temperature of the metallic part. It must be a metallic part. Which kind of materials, up to you, could be used in order to have what is very important here, a very high cooling efficiency, because you see, this is the part of the plasma formation which is direct in contact with the anode. We need to use the materials with a very high thermal, or if you want, electrical, that's the same conductivity. And so this selection is copper, okay? And even though the melting temperature of copper is not so high like those of tungsten, the cooling system can be designed in a very efficient way. That's an engineering problem in order to avoid melting of copper. And so the spare part of this torch are essentially the cathode of tungsten, instead the part of copper, which represent the anode, it works for the whole lifetime of the torch itself. Here you see, perhaps it's not so clear, but that's the circuit of the cooling water for the copper, this one, okay? This is the tungsten tip, that is the anode. And this is the same drawing of before, but it's a real drawing, I mean, a drawing over a real torch. Which are the parameters? Which are the parameters which can affect, let me say, this kind of technology? There are many, as we will see. Let's have a look to the most important in order to lead to you some guidelines. For sure, the primary gas flow of the plasma is important. Primary with the meaning I told before. In a sense, if we use a mixture of plasma gases, the primary plasma gas is that gas which is present at a higher percent. And also the secondary gas flow is important. Secondary gas for the plasma formation when used. Obviously, the plasma power is another parameter that we can expect will be very important because it affects ionization, that is plasma formation. But there is also, for example, let's have a look to this, the spray distance, which is very important. The spray distance, what is calculated as the distance from the exit of the nozzle to the substrate to be coated. Why this is important? Very simply, because the molten particles, which are melted inside the plume, if you let them travel for a long distance, they will solidify. So we need to adjust and to select the spray distance just to assure that the particles can impact on the substrate being still melted, not solidified. And according to what we said before, for example, in terms of difference between air plasma spraying and vacuum plasma spraying, we said that vacuum plasma spraying, the gas met less resistance, so the plume will be longer. So we can expect, for example, that for the BPS system, the spraying distance will be longer than that which is used for the APS. Of which kind of size we are talking about? Again, in this case, I cannot give you a fixed number because that depends on the power, on the gas composition, but just to have an idea, something which is around 20 to 25 centimeter, okay? That's the distance, 30 in some cases, the distance between the nozzle exit and the substrate to be coated. In some cases, also lower. In BPS, it can be a little bit higher, depending on the length of the tube. Then also the injector what is the part through which the powders are flowing, transported by a gas. So the carrier gas flow is important, we just discussed it before, but also the injector angle is important, as well as the length and size, because if this is the plume, sorry for my drawing, we can have injection in this way, we can have injection in this way, we could have injection in this way, that is a negative angle, and that's a parameter which must be adjusted in order to minimize the number of particles which go down here and the number of particles which are shielded by the plume, so does not enter the plume and that they represent dust, will not contribute to the coating formation. And then, well, the thickness of coatings per pass we just discussed. Also, the gun spray angle is important, because if we have a flat, just to represent to you, substrate to be coated, we could have a spray angle which is 90 degrees, or we could have a spray angle which is different from 90 degrees. And this is very important. You must think not to flat surfaces, which are a didactic cases, but think to the profile of a blade, okay? And so you need to adjust in order to avoid also, for example, that the dust, which is always present, would be incorporated inside the coatings and which will represent further defects of coatings itself. For the primary gas flow, what can be said? We are just entering on some guidelines, okay? We can say that increasing the primary gas flow usually will increase the gas velocity in the plasma jet, in the plasma plume. And this, obviously, if we do not change the particles, will result in an increase in the particle velocity. The faster the particles travel the jet anyway, shorter is the residence time, what is called here dwell time. That's the residence time inside the region in which they see thermokinetical exchanges. And this means that we can expect, you see, we have effects which must be balanced, so that it's just a real engineering activities, because in this case we could say, well, if we increase the primary gas flow, we can increase the velocity of the plasma jet. This would be fine because the particle velocity would be higher, and thus the residual porosity of the coatings will be lower. But at the same time, this causes a reduction of the dwell time, and so it causes a reduction in the final temperature of the particle itself. So we need to balance in order to have melting, in order to have the proper degree of melting. So from one side, in terms of density, increasing the gas flow velocity would be beneficial, but we could experience problems in partial melting of the powders, which results in poor quality of the coating itself. The secondary gas flow for the plasma formation, and usually for our applications, we have a mixture, we will see later, of two plasma gases, is important because it will influence the process voltage. For example, by using hydrogen, which is very commonly used, the voltage between the two electrodes will be increased. And so this can affect the plasma formation, and that can affect the plasma temperature, which is another important parameter because the plasma temperature controls melting. And for example, just to give to you a comparison, if we use an argon-helium plasma gas in terms of mixture, this will be colder than a pure argon plume, but then we do have some beneficial because the conductivity is going to be increased due to the presence of helium. But what I want to say, if you use an argon hydrogen, this will be hotter than a pure argon plume. And so usually the hydrogen is very often used in a plasma gas formulation. Our TBC are made by using hydrogen as a secondary plasma gas, because this can allow to us to reach the highest temperature values that I showed to you before, and thus to better control the melting process of the particles itself. Why? It's written again here, because the higher is the flame temperature, the higher is the degree of the particle melting. The spray distance, we already discussed before, why it is important. Here you have some more detail, but the basic concept is that we need to avoid resolidification of the particles. And when we are in the phase of development, for example, of a new coatings, we make experiments. So if we don't know already, because somebody has not yet worked on that, which are the best optimum parameter, for example, in terms of plasma gas composition as well as a spray distance, we make some trials. We make very flat specimens, which then will be observed under optical microscopy or scanning electron microscopy, that depends on the resolution that we want, in order to put in evidence the microstructure, that is, put in evidence this one, okay, and to understand if that kind of combination is suitable for us in terms of residual porosity, in terms of presence of melted particles, and the same applies also. Let me go again to that slide for the good definition, the best definition of the spray distance. Obviously, if we are talking about thermal barrier coatings or standard coatings like alumina, titanium, wear-resistant coating, very often used, we already know which are the parameters which can give to us the best results. The only thing that has to be kept in mind is that parameters are defined, how to say, for an as fabricated torch with anode and cathode with our in the original state. And so that one must be kept in mind, because the consumption of the cathode can alter the plasma formation, and that is the coating quality. Also, the plasma power is important, because obviously, I would say, if you increase the plasma power, for example, by increasing wire rate and by increasing amperage, because usually the electric arc is obtained by forcing a current intensity fixed. which will result in a voltage, in a difference of voltage between the two electrodes. But if we increase the plasma power, we increase the process temperature. This obviously will increase the flame temperature, and so can have the possibility to melt better, or to melt materials having a higher melting temperature. But this must be considered together with another aspect. First of all, we cannot think to increase the plasma power at infinite level, otherwise we will destroy our torch. And remember that of the plasma, let me say better, of the powder, of the power that we put inside the torch, have in mind the temperature, we have said, have in mind the necessity to cool the electrodes, just some few percent is the power which is used for the process, that I mean for melt the powders. The other one is power loss, and this affects obviously the cost of the spraying process and the cost of the manufactured object. So we can increase the power as we want because we do have problem on materials, and that's obvious, but also because the quantity of power loss will be so high that the process can become economically convenient. I would stop today here, and then we will discuss about the importance of particle velocity from the next meeting, which will be on next Monday. Okay? Yeah. All these slides are already on your Google Drive, so you can have a look at them. Okay, for today, I think it's enough. Let me go out. Okay, if there are some questions, I'm here to answer. No questions, so see you on next Wednesdays. Arrivederci a tutti, bye bye to all.